Well, good afternoon. It's 12:49. We're 19 minutes late getting started, but no one's in the room but me. I was just talking with Dr. Bryant. No one was in his class either. That's why he came over and started chatting, and that's why I'm late getting started. But we'll go on and get started now, if I can get the system to come up. And I wanted to let you know, if you had been noticed, if you've been trying to follow YouTube videos at home, I don't know if it's Screencast-O-Matic, I don't know if it's YouTube, I don't know who it is or who's at fault, what's going on here, but it seems like in the afternoons, either Screencast-O-Matic won't load or YouTube won't take them. I don't know which is the problem. But it happened, I think, Tuesday, Wednesday, and Thursday of last week. In the mornings, they load great, okay? But in the afternoons, they just won't load. And my morning class this morning, 10 to 11:40, by the time I was teaching my next class, and that one should have been loaded, it had not loaded either. I don't know why. I cannot guess why. So if you aren't seeing these on time, wait a day or two, and usually they do get caught up. But I don't know why they're not loading. They had been just like clockwork. You know, I put them in, and by the end of the day, everything was loaded. Maybe not the last class, but everything else. Now they get 50% and stop. So 50% is processing on my end. The other 50% is sending to YouTube. That's where it ends. So anyway, enough of that. I'll wait and do announcements till someone comes in, if someone comes in. But let's go on and pick up where we left off last time. We're in Chapter 2, First Order Differential Equations. 2.5s are solutions by substitutions. And here's example 1 on page 73, about the middle of the page. Solve this. Whoops, let me get my pen set up. X squared plus y squared dx plus x squared minus xy sorry. So sorry. That can't sound good. dy is equal to 0. Now, that is what we have last time we're calling a homogeneous equation, because every term everywhere is degree 2. X squared is degree 2, y squared is degree 2, x squared is degree 2, xy is degree 2, 1 and 1, 2. Okay? Now, this would be our m of xy. This would be our n of xy. Okay? Now, if we were trying to do this by exact, what we would do is partial of m with respect to y, and that would be 2y. And if you did the partial of n with respect to x, that would be 2x minus y. Not the same, okay? So you can't do it by exact methods, okay? So that is out of the question, okay? For some reason, my eraser quit working, okay? And it's just doing whatever it wants to do. This system is going bad. Okay. All right. It seems to have found itself. It got lost somewhere there. Okay? So here we're doing, we make the substitution. since that's what we're doing, solution by substitution, that we talked about last time, okay? If we let y is equal to ux. Now remember, the other possibility was x equal vy, okay? One of those two, okay? Let's just try y is equal to ux, okay? I wish I could give you a magical reason of which one to choose first, but that's what we're going to do. I can't, so we're going to do this. Then based on this, dy is equal to partial of u with respect to y, actually, no, let me not change this for right now. Rearrange this, okay? U dx plus x du. Okay, that's how they approach it. Now, that's what your dy is. This is what your y is. So here we're making the complete substitution and getting to a differential equation in u and x rather than, well, let's just plug in and get it. So this would be x squared plus u squared x squared, okay, that's your y squared, dx, okay, plus x squared minus x squared u, because u times x times y, and y is ux, so that would be that one. And then your dy is u dx plus x du, and this is equal to 0. So you see, every y we plug this in here and here, and every dy we plug that in. So now we got a bunch of manipulation to do. So let's do that. X squared plus u squared x squared dx plus, now, no super easy way to do this, so I'm going to try to do it this way, okay, like this. X squared u, and I'm going to do my dx's together, minus x squared u squared dx, okay, and then do the same thing here, and that would be a plus x cubed, that would be this one times that one, minus x cubed u du, okay? Now, if you take a close look at this, here you have a plus u squared x squared and a minus x squared u squared here, dx's. So those add away, and this gives you an x squared plus x squared u dx plus an x cubed minus x cubed u du is equal to 0. Okay? Now, all right. Now, notice this term has x squareds in both terms, so that would be x squared times 1 plus u dx plus x cubed times 1 minus u du is equal to 0. Okay. Now, what we're going to do now is separation of variables, so to speak. Okay? We'll divide this term by x cubed, both terms by x cubed, and this term by 1 plus u. Okay? And that would yield one over x dx, and frankly I'd rather move this to the other side and say this is equal to u minus 1 over u plus 1 du. Okay. Now, before we do anything else, let's and they mention in the book, do long division here. U plus 1 into u minus 1. Okay? Well, u will go into u one time. That will give you a u. 1 times u is u. 1 times this is plus 1. Subtract and you get a, which is the same as change signs and add, minus 2 as a remainder. So it would be minus 2 over u plus 1. Okay? So this one, that's what this becomes. 1 minus 2 over u plus 1 du. Okay. Now, if you integrate both sides of this, this gives you, I'm going to come up here to do it, log x, I'll put absolute values on that, is equal to u minus 2 times the natural log of u plus 1. Okay? And then we need a plus c in there. I don't have room to write it, but we will do with that in a minute. And I think this is probably a good place to put that constant in, but we're going to put it in as a log c. That's a constant. It's just a different way to do it. Okay? Now, what is the u? Well, u is equal to y over x. Okay? So, rejoining things here, you might say, this will be, I'm going to bring this to the other side, so this will be a log of x plus the log of, and then instead of u, I'm going to put y over x plus 1 squared, okay, is equal to y over x. That's your u there. Okay, oh, and I meant to do, I'm going to put plus log c here. I know the sign doesn't look right. It's really a minus log c. But if you combine these things together, you get, and that is y over x, not a u over x. And if you put denominators in, that'd be y plus x over x. I hope that's okay. So what we have here is cx times y plus x over x is equal to e to the y over x. Okay. Oh, I forgot. This was squared here. Sorry about that. Okay. Well, here, since this is going to be an x squared, this will be an over x then. Okay. And then we can multiply, and actually I should have left the log c on the other side, but we'll worry about that in a minute. So this gives us a y plus x squared is equal to, and I'm going to make that c a 1 over c so I can multiply it through here. And to c x e to the y over x. I don't know why the thing is being so uncooperative today, but it is. The screen keeps going out on me. I think it has something to do with the fact power fluctuates in this room in the afternoon. Or at least that's what I thought until when I was in Georgia over the weekend at a very slow DSL line. It wouldn't load in the evening, and it loaded in the morning with no problem. So I don't know. I just do not know. Okay? But anyway, that's what they get. Now, they wrote theirs as x plus y squared. I wrote it as y plus x squared. It really doesn't matter. It's equal to c x e to the y over x. And that's what we got. And for some reason, I guess from my sneezing before, now my nose is running like a fountain. So excuse me just a minute here. Okay. But that's your substitution that we use with homogeneous or homogeneous equations. That's when they all are at the same degree, every term on both sides. They look like a exact equation, but when you try it, the exact equations don't work. But if they are homogeneous or homogeneous, then try this technique, y is equal to ux or x equal vy, and go through and see if those will help clean up the situation. Now, although either of the indicated substitution can be used for every homogeneous differential equation, in practice we try x equal vy whenever the function m of xy is simpler than the n of xy. So there came the reason. If this m of xy was much simpler than n of xy, then use the other one, x equal vy. Okay? But if they're about equal simplicity or n is simpler than m, then either, if they're equal simplicity, it doesn't matter which one you use. But whichever one is if the m is simpler, use x equal vy. If n is much simpler, use y is equal to ux. Okay? That's sort of the rule of thumb. Although it could happen that after using one substitution, we may encounter integrals that are difficult or impossible to evaluate in closed form, switching substitution may result in an easier problem. Notice the may there. No guarantee it will, but it may. Goodness me. Nose is itching. Okay, let's move on to Bernoulli's equation. Okay, now this may look similar to what we have done, but it is a slightly different form. Here's what it looks like. A dy dx plus p of x y, oh, this looks like a linear form, doesn't it, is equal to some f of x times y to the n. Whoops, there's where the linear form, it goes completely haywire, because the linear form just had a f of x there on the right hand side, not a y to the n. Now, dividing by y to the n would put a y function back in for the p of x, but that wouldn't help us any because it needs to be just a linear y there. Now this is good whenever n is any real number, not just integers, not just positive integers, but any real number, okay? And it's called Bernoulli's equation. Now, if that n was 0, you just have a linear form. Okay, if n is 1, you just have a linear form. Okay? But if n is not 0 and not 1, then here's the substitution we use. U is equal to y to the 1 minus n. Okay? And that will reduce this equation to a linear form, a linear equation. So let's see if we can do that substitution here. Okay, I'll erase what I've got, hang on to the thought of what we had before. Here we have x dy dx plus y is equal to x squared, y squared. Okay, now, with that kind of equation, you never want this function in front. Now, before we do anything, certainly we don't want x being 0. Because if x is 0, you just have y is equal to 0. So that's just a trivial solution. Yeah. It doesn't give you anything, okay? So that's not going to be an issue. Since that can't be an issue, then what we're going to do is divide everything by x, because we do want to get it into a standard, more standard form. So this gives us dy dx, that's how we want it to look, plus 1 over x times y, that's how we want it to look, is equal to xy squared. Now the x would be fine for a linear form, but not with y squared in there. Okay? So if you remember what they just told us the substitution should be, let u equal, on the previous page, y to the 1 minus n. And our n here is 2. So this would be y to the minus 1. Okay? That's what our substitution is going to be. U is equal to y to the minus 1. Okay? So du is equal to minus y to the minus 2 dy. Okay? So dy is equal to minus y squared du. It feels like we're running in circles here. And actually, they didn't quite do it the same way. So let me back up and it the same way they did, just so I won't waste as much time. Okay? You could do it that way, but let's do it the same way they did. That should be the more efficient way. Okay? So they have u is equal to y to the minus 1, which also implies that y is equal to u to the minus 1. Because if you multiply both sides of the first equation by y, that gives you yu is equal to 1, and then divide both sides by u, and that gives you y is equal to u to the minus 1. Okay. Now, what we have up here is the dy dx. So that's what we want to do next. Dy dx is equal to minus u to the minus 2 times du dx. Okay? Well, no, they're going to do something more generic to begin with, because that isn't exactly where we want to go. Okay? The generic form here is that's equal to dy du times du dx. Now, almost, basically the same thing, which is dy du is minus u to the minus, it's the same place I was, times du dx. Okay. So what we're going to do is put that in up here to this equation. So this is going to be minus u squared, u to the minus 2, du dx plus 1 over x times y, which is 1 over u, and that's equal to x times 1 over u squared. Okay, I believe that's it. Okay, now, let's divide or multiply both sides of this by minus u squared. So that gives you du dx plus, or minus now, multiplying both sides by minus u squared. That would give you minus u over x is equal to x minus x. Okay? So you could rewrite that as du dx minus 1 over x times u is equal to minus x. Okay. Now, remember our linear technique then. This is what we call the p of x. P of x equal minus 1 over x. And we integrate that, dx. Integrate that, dx. And this will be minus the log of x. Okay, and we don't ever put a constant on that. Okay, and then we e that. Well, let's rewrite this as log of x to the minus 1. And then you do the e of that, which is the e of this, which would then turn out being 1 over x. That's our integrating factor. okay? So we take this form here and multiply it. du dx times 1 over x minus u over x squared is equal to minus 1. The minus, I guess the minus is still right, okay? Now that's supposed to be, if everything worked out well, that's supposed to be u, the derivative of u, which is 1 over x times u. Okay, well, let's see if it is. That would be 1 over x times du dx, that part right, plus a minus 1 times u to the, yeah, that works perfectly, and that's equal to minus 1, so do your dx over here, and what we have now is u over x is equal to minus x. I believe here is where we put in our plus c. Okay? So that would give us u is equal to minus x squared plus cx. And the u is y to the minus 1. So 1 over y is equal to minus x squared plus cx. If we multiply both sides by y, you get minus x squared y plus c xy is equal to 1. I think that, well, that's one way of expressing it. The other is from this form, taking that to reciprocate both sides, y is equal to 1 over a minus x squared plus cx. Okay, and that's what they got in the book. Y is equal to 1 over a minus x squared plus cx. Now again, y is equal to 0 would be a singular solution, so that we can't say that's a general solution yet. Because when y is equal to 0, dy dx would be 0, y would be 0, y squared would be 0, everything would be 0. So, now, let's look at one more sort of technique. We talked about substitutions in general, then homogeneous equations, or homogeneous equations, then Bernoulli's equation, which we just did. Now we're going to reduction to separation of variables. Okay, so let's clear the screen here. And let's write a new form, differential equation of this form. dy dx is equal to some function of ax plus by plus c, okay, can always be reduced to an equation with separable values by means of the substitution let u equal ax plus by plus c. All right, that's going to be the substitution we use here. And before I do example 3, all that sneezing I was doing has really loosened my head. I need to just run down and clear my head one more time. So let me put this on pause and I'll be... All right, sorry, I had to run down. I had to clear my head. Got it somewhat clearer. But the other thing is I realized since I didn't have a student in here and didn't have a watch on, I needed some way to tell when I was running out of time, so I went to the office to get my cell phone, so I'll be able to check on that. So let's do example 3, which happens also to be an initial value problem, but that's sort of beside the point here. It's the technique that we're working on, but we'll use the initial value at the end. So let's solve this. dy dx is equal to minus 2x plus y squared minus 7. Okay? And the initial value when y is equal to 0, when x is equal to 0, y is equal to 0. Okay, y of 0 is 0. All right. Now, here your dy dx is some function of a linear combination of x and y. That linear combination being and by the way, on the earlier one, when I wrote that down, the substitution, the b can't be 0, by the way. The y has to have a coefficient. And here the coefficient happens to be a 1. Okay? So your u substitution, your f function here is x squared, well, let's start with the u substitution. Let u equal minus 2x plus y. The c here would be 0. Don't bring in the minus 7. Okay? Okay, and just like with most substitution, our next step would be then du is equal to minus 2x U's a function of x, by the way. Okay. Minus 2 dx plus dy dx. Okay. All right. Okay. They write it a slightly different way, so let me go back and write it their way. They don't split up the way we used to in this way. dy dx is equal to minus 2 plus dy dx. Okay, that'll be a little bit easier, more palatable to work with. Okay. Now, so with that is our u transformation, and I think we ought to go on and do this too. The dy dx is equal to du dx plus 2. And I think up here we probably should do the y is equal to u plus 2x. Okay. Because we want to get rid of the y's. Okay. So the dy dx is du dx plus 2 is equal to u squared, because that was your u squared, minus 7. Okay. So we really didn't need this part at all here because we didn't have a y by itself. Okay? Now, let's get things together here. du dx is equal to u squared minus 9, subtracting 2 from both sides. Then use separation of variables here, and of course u can't be plus or minus 3, okay? So we'll have to deal with that in a minute. But du over u squared minus 9 is equal to dx, okay? Now this one I think we'll do partial fractions, and that will be 1 over u squared minus 9 is 1 over u plus 9 plus 3 times u minus 3, and we'll have that being a over u plus 3 plus b over u minus 3. Okay, multiply both sides by that product, and that will go out, and this will be a times u minus 3. This will be plus b times u plus 3. Okay? Now, how we go about solving that is letting u equal 3 to begin with, and that would be 6b is equal to 1, so b is equal to 1 over 6, and then we could do u equal minus 3, and that would be minus 6a equal 1, and that would be a is equal to minus 1, 6. So then this would be 1 over 6. Okay, we're going to integrate both sides of this, okay? And this would be 1 over 6 times the integral of du over u minus 3 minus 1 over 6 times the integral of du over u plus 3, and that's equal to x. Integrate that. And we'll put a c out here, but it may turn out being a log c, it may turn out being 1 over c, we'll figure that out in a minute. So this would be 1/6 times the log of u minus 3 over u plus 3. Let's see what happens if we just do x plus c to begin with. Okay. Let's take this inside and make it to the 1/6 power, and then e both sides, and you have u minus 3 over u plus 3 to the 1/6 is equal to e. I'm going to change that e to ce to the x, because e to the x plus c is e to the x times e to the c, and just make another c to be e to the c. Okay. Now, the question is, do we go back to what our y's are now, or do we try to simplify this sum? And let me see. Sorry. My screen's just disappearing on me. I don't know why. Okay. It'll come back, I think. I don't know what it's doing. I'm not touching a thing. It's just flicking on and off the way, however it wants to. Okay. I don't know what to do now. I'm going to minimize that. I don't know. I have a feeling it's going to erase everything I've got. So what I'm going to do, I'm going to tell you what I'm going to do. I'm going to raise both sides of this to the 6th power, which means c to the 6th is just going to be some new c, and e to the 6c. So that's what we're going to do, but I don't know what's going to happen here. Okay. I'm going to have to come back in. I don't know why it did any of that. I wasn't touching a thing. It was just clicking on and off and flipping around to wherever it wanted to do, and now it's acts like it's having a hard time opening again. Let's see how much time we have left. 2 minutes. So let me see if I can get this done in 2 minutes. Okay. You have to remember where we were before. Let me get my pen back. Okay. We had it something looking like this. Log of u minus 3 over u plus 3 to the 6th, no, to the 1 over 6, is equal to x plus, I just said a c, they call it a c1. Take the e of both sides, and you get u minus 3 over u plus 3 is equal to e. I'm going to change that to ce to the x. Now, how you do that, if you did this, then this is the same as e to the x times e to the c. Well, e to the c is just some constant which we're going to move in front. Okay? And this was to the 1/6 power. And this is what I said. I'm going to raise both sides to the 6th power. That gives you u minus 3 over u plus 3 is equal to c to the 6 is some other constant c, e to the 6x. Okay? Now this is sort of an exercise in frustration, but it does work. Okay? Multiply both sides by u plus 3. So you got u minus 3 is equal to u plus 3 times c e to the 6x. Okay? Now, multiply through. You get u minus 3 is equal to c u e to the 6x plus 3c e to the 6x. Okay? Let's get all your u's together. That would be u minus c u e to the 6x is equal to 3c e to the 6x plus 3. Okay? Divide out our u is equal to, u times, 1 minus c e to the 6x is equal to 3 times 1 plus c e to the 6x. I rearranged a little bit there. So you get u is equal to 3 times 1 plus c e to the 6x divided by 1 minus c e to the 6x. Okay. Now, this is what we go back and use our substitution. U is minus 2x plus y. So minus 2x plus y is equal to 3 times 1 plus c e to the 6x over 1 minus c e to the 6x. And then add 2x to both sides. You get y is equal to 2x plus 3 times 1 minus c e to the 6x over 1 plus e. No, I got them backwards. Plus on top, minus on bottom. C e to the 6x. I think that's the answer. Y is equal to 2x plus, they put the 3 up with the numerator, but it's okay. 1 minus, okay. Okay. I haven't used my, because I went to a new thing, I forgot we had an initial value problem. Y of 0 is equal to 0. Okay. So, let's put in a 0 for the x. Okay. And you get y, or you get 0 is equal to 0 plus 3 times 1 plus c over 1 minus c, because e to the 0 is 1. Okay, so that would give us 1 minus c is equal to 3 minus or plus 3c. Get your c's to one side, and that would give you 4c is equal to minus 4, c is equal to minus 1. So now if you put that into this form, this will be 2x plus 3 times, when c is minus 1, that changes the sign of this one, 1 minus e to the 6x over 1, and c to the minus 1, make that plus e to the 6x. Okay, there's our solution. They put the 3 in the numerator by itself with the other. So there we have it. That finishes section 2.5. Homework exercises here would be do any of the odds 1 through 13. There are homogeneous equations, either 11 or 13. Those are two initial value problems. I'll let you figure out. They look like they're homogeneous to me too. Then any of the odds 15 to 21, those are all, now 15 to 19, those are all Bernoulli equations of some form or another. 21 is a Bernoulli's equation initial value problem. And then 23 through 27 are linear substitutions. That's any of those that are in the back of the book can be done. And 29 is a linear substitution with an initial value problem. And then discussion problems, most of the time those are not in the back of the book, but you can certainly do any that are. If none are back there, don't worry about it, but I would pay attention to number 35. There's a differential equation called Riccati's equation, and you could write on who in the world is Riccati, or how did he come up with this equation, or where is this equation used. And by the way, you could do the same with Bernoulli, figure out which Bernoulli came up with this Bernoulli's equation. There was a whole family of Bernoullis. 2 brothers, and they all had sons, and so see which one that was, and you can write on Bernoulli or how he developed or who uses Bernoulli's equations, and then we'll go from there. We'll start next time with 2.6, okay, and that's where we'll begin on Wednesday, okay, at the beginning of the page there. So, sorry no one showed up. Since no one was here to hear an announcement, let me just quickly go over those. If you are in a first mini-term course, remember The student course evaluations are open now. Please do those. They usually leave them open a little while after the term end, so you should be able to have a chance to get those done. Do them as soon as you can. So that's that announcement. Also, since we have, and this is beside the point, I was going to say it's going to be midterm this week, and then midterm progress reports will follow that. But both of you have turned in your first test, so you have scores. I encourage you to work on your research papers. That's one reason I was mentioning potential topics there. Be sure you do your research paper as well. You don't have to have that in by midterm, but if you didn't have a test in, that would be another option. One other thing, well, a couple other things. My personal schedule, if you're looking for me tomorrow, I'm in class just about all day Tuesday and Thursday, but tomorrow I've got a doctor's appointment that I have to leave campus by 9 and probably won't get back until somewhere close to 12. Hopefully before 12, but hopefully not too much later than 12. It's hard to say with doctor's appointment how fast they'll be, when you'll get out, that kind of stuff. Okay, so that's tomorrow. Wednesday should be a normal day, so we'll be here in class. Hopefully someone will be here besides me. And but then Thursday, when we don't have class again, I have a meeting in Tuscaloosa that I'll be going to, and I won't be on campus at all in the morning. However, I will be back hopefully sometime maybe around 4:30 or so. I'll be here from about 4:30 till 6, because the meeting's supposed to be, it's in Tuscaloosa, it should be over about 3:30. I hope I can be back in an hour, and so I should be back from 4:30 until around 6. No guarantee of that, but I think I will be. So anyway, then Friday should be a normal Friday on the Birmingham West Campus, 8 to 12. The only exception is I do have an appointment in the afternoon on Friday, but I think it's late enough that I won't have to leave before 12. But anyway, weird week, too many things, 2 doctor's appointment, 1 out-of-town meeting. So anyway, that's it. Oh, and one more thing. Tomorrow is primary day. I hope that both of you are registered to vote, and I hope you're planning to vote. Please vote. Do not pass up on an opportunity ever to go to the polls and vote. So please take advantage of your right and your responsibility to vote. Thank you. We'll see you on Wednesday, I hope.